Okay, so in this movie clip, let's briefly review what we have learned for the reverse biased PN junction diode. So since this PN junction diode is reversely biased, the total amount of current is very small, negligible compared against the forward biased current flow in PN diode. So as we have learned, in a reverse biased PN junction diode, oops, reverse biased PN junction diode, as we know, there is negligible, very tiny amount of diffusion of majority carriers across the junction. You know the meaning of it, right? If I draw the cross-sectional view of a PN junction diode under forward biased, now you can see under biased PN junction diode, and as we have learned, that the hole can be injected into the N-type region, and these holes can be diffused out throughout the N-type quasi-neutral region. But if this applied voltage is reversed, then the potential energy barrier between P and N region has been increased a lot, so this whole injection can be blocked. Okay, so this whole diffusion, the diffusion of majority carriers in this N region, that means that this hole is negligible. So the reverse saturation current, so in diode equation, that was I naught, right? So the reverse bias, the saturation current comes from what? Yes, the drift current of minority carriers across the junction. So going back to the energy band diagram of PN junction diode under reverse biased one. Under reverse bias, the PN junction diode's band diagram has been drawn as follows, right? And as we have learned, this is a p-type, this is an n-type. So the uh, electrons in this p-type region, right? These electrons can be diffused into the right-hand side or left-hand side with a 50% probability if this electron is limited into a x dimension only. Then, under reverse bias, the minority carrier, the minority carrier, this electron in p side can move across this PN junction region. Okay, once it is injected into the depletion layer. Why is that? Because in this depletion layer, the built-in electric field has been well formed. So the electron moves like that. So this drift of electron from p-type region or drift of minority carrier in p-type region across the junction is the main origin of saturation current I naught. Definitely in the n-type region, the minority carrier hole can be injected into the depletion layer and it's going to move like that, and in the end it can arrive into the p-type region. So this minority carrier in n-type, which is a hole, is another origin of saturation current. So we have learned it, and this saturation current I naught is very dependent of what? Yes, the rate of minority carrier generation rate of minority carrier near the junction. So let me change my color. Take a look at here. How many electron has been thermally generated near the or at the edge of the depletion layer? And then these thermally created electrons would be injected into the depletion layer. Then that would be the physical origin of saturation current. So this generation rate of minority carrier close to the junction region is very, you know, the key driver in determining the saturation current in PN diode. So as described here, the saturation current I naught is very dependent of the generation rate of minority carrier close to the junction. Okay, more specifically, how close to the junction? Then you can say that within one diffusion length of depletion region. So from the x of minus xp, and here x is minus xp minus ln. So n is electron in the p side is my energy carrier. So minus xp indicates the edge of the depletion layer onto the p side, and minus ln means one diffusion length away from the edge of the depletion layer. So within this region, right, x is minus xp minus ln to minus xp. Within this region, if we if the thermal thermal generation rate of minority carriers, which is a thermal generation rate of electrons in p-type region, has been increased a lot, then we may expect very increased saturation current. Okay, so as we have learned, you should review the physical origin of saturation current of PN junction diode under reverse bias. Okay, so take a look at this sentence here. So we can increase this reverse current, saturation current I naught, by what? By increasing the rate of minority carrier generation. But the question is how to increase the rate of minority carrier generation. What is the right ways to increase the rate of minority carrier generation? So for example, there are two ways. Number one, optical excitation of carriers. And this method, this approach can be well adopted for photodiode application. And second way to increase the rate of minority carrier generation in PN diode under reverse bias is electrical injection of minority carriers into the vicinity of the junction, close to the junction, right? So close to the junction, if we can enhance the generation rate of minority carriers, in other words, if we can gear up or place a certain new magic box right onto the P side region, right, under reverse biased one, that is definitely reverse biased one. So if I put a new magic box into the P side, and the role of this new magic box is to inject the minority carriers, the electrons, into the depletion region. So if I can increase this injection rate of electrons in PNP type with the help of new magic box, then that would be very good news. And the question is, what should be like? What is the real one for this new magic box? Can you come up with your own idea? Pn. You want to increase the rate of electron should be moved into the n-type region more. How to do that? Yes, by placing M plus region, and this PN diode is forward biased, then more electrons can be injected into the p-type region, right? Once this PN diode has been well forward biased, the majority carriers in N side can be well and smoothly, easily injected into the P side region. As we have learned, forward biased PN diode, we can expect exponentially increasing current. Then those electrons can be a good resource to be injected into the N side region, right? So the question again is, we have a PN diode, and we would like to increase the number of electrons from P to N. Definitely this PN diode is now under reverse bias. What is your own magic? What is your own engineering solution? Number one is optical stuff. So let me explain it later. What is the way, electrical method to enhance the total number of electrons into the n-type region from P? under reverse bias. How to do that? Yeah, we need to put a new magic bars which can supply huge amount of electrons into the p-type region. Then the since this p-n diode is, even though this p-n diode is a reverse bias, if we can supply a humongous number of electrons into the p-type region, then that would be possible to enhance the injection rate of electrons from p-type. What is your real thing? How to implement your idea? This new magic box can become n plus reason or n reason even. That would be okay. Anyhow, any semiconductor material which can contain more number of electrons, that would be n-type or n plus happily doped one. So this n plus reason has been placed right onto the p side, and this p-n junction, another p-n junction, right, is under forward biased. Then we may allow many electrons get into the p region. So take a look at this shape, NPN. This is NPN BJT. And in this NPN BJT, if you'd like to increase this saturation current, then you should do forward bias the first NP region. So forward bias, reverse bias, both are used together to do something magic. So we're gonna study that later. Anyhow, herein, the thing that I would like to deliver to you is how to increase herein the thing that I would like to deliver to you is how to increase the rate of minority carrier generation close to the junction. Think about this issue. And if you have successfully come up with your own idea, then you're ready to develop your own BJT device. Okay? So try to have your own time to understand why this electrical injection of minority carriers into the vicinity of the junction would be the answer and engineering solution in increasing the rate of generation rate of minority carrier close to the junction. Think about this issue. Okay. All right. And before stopping this movie clip, I'm going to briefly tell you how come this optical excitation of carriers would be the good option and good way to increase the generation rate of minority carrier under forward reverse bias. Let me draw the electric current versus voltage. Current versus voltage of PN junction diode. And you know the ideal diode equation is. The question is you would like to increase the saturation current to I naught. So let me change my column. So you would like to increase your I naught up to here. So previously this, but now your saturation current has been increased a lot. Then your IV curve would become like that. So the question is, what is the physical origin for increasing the saturation current I naught? Herein, optical excitation of carriers would be the way for increasing saturation current. How to do that? If you injecting photons into the p-n junction diode, that photon is kind of, a mass of energy stuff. So those energies can be observed into the p-n junction diode, and normally generated electron hole pairs are created a lot here and there occur throughout the p-n junction diode. But those, the carriers, normally created carriers close to the junction edge would be well injected into the other side or into the depletion layer, so that you may spontaneously expect the increased saturation current. Okay, so by shining light onto the PN diode, And most of the electrons and holes, the minority carriers normally generated close to the junction would be the good physical origin of this increased saturation current. Okay, but the more the point that I'm more interested in is this. Take a look at this part. The current is negative and bias is positive. The power is defined as voltage times current. But in this regime, if your PN diode is operating at this point, then this power is negative. What does it mean? Maybe in linear circuit theory or in circuit theory class, the very first chapter has introduced how to estimate the power consumption for each passive elements in your circuit, such as resistor, inductor, and capacitor. Usually, the passive elements can consume the power supplied from the voltage source, current source, and others. But in this PN junction diode is a type of passive element used in microelectronic circuit. And this passive element is not linear, but not linear. That sounds weird. Anyhow, RLC, resistor inductor capacitor, is a linear component in electronic circuit. But this PN junction diode is one of the representative ones in terms of non-linear devices. Think about the diode equation again. Current I is defined as something I naught times exponential to the VA over KT over Q minus 1. So VA versus I, that is very non-linear. So that this nonlinear device can be used to create what? To generate the power in microelectronic circuit once it is exposed to the light, definitely. What is the final product of this concept? Yes, solar cell, right? So solar cell is basically PN junction diode exposed to the light. Once PN junction diode is forward biased and it is exposed to the light, then it can generate the power. Why is that? The PN diode is forward biased. The higher voltage is applied onto the P side and lower voltage has been applied to the N side. But the current direction is from N to P. So this nonlinear device PN diode or a solar cell can create and generate the power. So if you combine many cells into as a module of the kind of module or solar panel or solar module, then it can be used a power generator. So recently, as a renewable energy source to replace uh, a conventional power resources, many government fund has been supplied to the consumer field, and many people has built up solar farm, right? Solar farm uh, can be well observed and well can be shown in rural area. If you have any chance to travel rural area, you may see that many solar farm has been well developed and built onto the mountain or onto the side of the mountain or even a small field. Very not looks ugly, but the not very well developed field has been covered up with many solar panels, and that would be the good that would be the a local power generator throughout the Korean peninsula. Anyhow, so going back to the main topic of this lecture note, in this lecture note, please have your own time to review how the current has been flown in a reverse biased PN junction. And herein the question is how to increase the saturation current. There are two ways. One way is the optical one, right, by shining light onto the PN junction diode, we may have a chance to increase the saturation current. But that's a kind of beyond of the scope of this lecture. This lecture is mainly focused on the IC devices, not solar cell stuff. So okay, the optical excitation of carriers, that is a good way to increase saturation current, but that is beyond the scope of this lecture. And the second approach to increase the uh, thermal generation or generation rate of minority carriers close to the junction is electrical injection of minority carriers into the vicinity of the junction. So that magic box was, it turned out that the magic box was simply, M plus region. And that M plus region can be placed right onto the P side. And that newly created M plus P junction should be forward biased. Then we can have a huge resource to supply humongous number of electrons into the N side. Okay. So that's all for this movie clips content, and please have your own time to review and think about what is the main solution to increase generation rate of minority carrier close to the junction under reverse biased PN diode. That is the main topic of this in this movie clips. Please have your own time to review it. And in the next upcoming movie clip, I'm going to deliver some more details how the PMP bipolar junction transistor is working. So more quantitative analysis with some detailed complicated equations is to be introduced. However, before moving forward, let's think about how the PMP BJT to bipolar junction transistor can work. So in the next upcoming movie clip, I'm going to deliver you the basic operational principle of PMP BJT. So please review the previous lecture note and see you in the next movie clip. Thanks for your attention. Bye bye.